Hi, welcome back. In this video, we're going to talk about the rules of transforming a function. And by function, I'm going to specifically focus on a quadratic. So we will be looking at the changes done to a quadratic function, and in particular, the parent function. Now, we can also focus on the square root function. It looks more like this. We can talk about the cubic function. We can talk about the cube root function. And even like the absolute value function. These are the most common functions we're going to be talking about. So the changes that we talk about today will be primarily for this one, the general function of a quadratic, right, which looks like x squared. And but just know that these rules are also applicable to all of these other functions or any parent function that we talk about. So let's get right to it. By a, we mean what happens if we have a function where x squared is being multiplied by a value. Right? What is the effects of this function? What is it going to do to it? So let's talk about an example. Let's say we're dealing with, if we want to graph the parent function x squared, this is what it would look like. I'm going to plug in 0, 1, 2 as an example. When I square 0, I get 0. 1 squared is 1, and 2 squared is 4. 0, 1, 1, and 2, 4. Now, the quadratic is a symmetrical function, so we can reflect this function over the y-axis to get the other values. Right? A quadratic looks like a U. Now, the minute I multiply it by something, let's say that we have a 2x squared. If I wanted to multiply by 2x squared, let's see what it does to the function. 0, 1, and 2. If I plug 0 in here, 0 squared is 0, times 2 is still 0. 1 squared is 1, times 2 is 2. 2 squared is 4, times 2 gives me 8. So this is what the function looks like. At 0, 0, there's no changes. At 1, I go up to 2. And then at 2, I would go up to 8 somehow. A little bit up here. And now this parabola will get a little bit narrower. Right? As you can tell, this point moved up a little bit higher. And then this point moved up even more. So we call this a vertical stretch because the function was stretched vertically. Or in other words, it got narrower. Right? So when the a value is greater than 1, if I multiply by 3, by 4, by anything in the front by a number greater than 1, I'm going to get a vertical stretch. Right? The function is going to get narrower. Now, what happens if I multiply it by, let's say, 1/2 instead? Let's try the same thing. Let's see what we get here. 0, 1, and 2 are my inputs. 0 squared is 0, times 1/2 is still 0. 1 squared is 1, times 1/2 is 1/2. 2 squared is 4. 4 times 1/2, I get 2. So when I plot these points, I get 1, 1/2. At 2, I'll get 2. And I can mirror this function. Something here. This should go to this point. And then in the other direction, I also go through 1/2, 2. Notice how this function looks wider than the original function. And again, my original function being this blue one. Right? I'm comparing everything to this function right here, the parent function. As you can see, this point was now pushed downward. It got compressed. It got pushed downward, right? So we call this a vertical compression. Since a was a number between 0 and 1, let's say 1/2, 1/3, 1/4, right? In this case, 1/2. We would call this a vertical compression, right? It got wider. Now what happens if I multiply the function times a negative? Right? Let's take the same values and let's look at the effects. What happens when I multiply by a negative? Well, 0 squared is still 0 times the negative 1 gives me a 0. There's no negative 0, right? 1 squared is 1 times negative becomes negative 1. 2 squared is 4 times a negative is negative 4. So when I multiply the function by a negative value, all of the points will now go down towards a negative. And now the function is pointing downward. Right? So this is what we call a vertical reflection over the x-axis. So when a was negative, or when a is less than 0, we have a vertical reflection over the x-axis. The effect of this value here, a, will make all kinds of vertical changes. It's going to affect the function vertically. And as you can see here, when we multiply by something greater than 1, it stretched the function higher, made it narrower. We multiply by 1/2, it made it smaller, it compressed it towards the x-axis, right? It pushed it down. And then by a negative value, it flipped it over completely over the x-axis. Let's talk about the changes of a different value. Here, we did, our general function will be f of x equal a bx minus h plus k. When you multiply the equation by something in the front, these are the effects. Let's talk about b now. What happens when I multiply by something with b, where b is part of the thing that's being squared? We're going to compare this again to the parent function. So let's graph the parent function. All of these effects are going to be comparing to the parent function. So what happens if I have f of x equals b of x squared, right? I'm multiplying it by b, some term. So let's try it. If I multiply this by, let's say, 2, what happens if the function is 2x squared? Well, let's graph the points. 0, 1, and 2. 0 times 2 is 0. Squared is still 0. 1 times 2 is 2. Squared, I get 4. 2 times 2 is 4. Squared is 16. Right? I got to do what's inside the parentheses first, and then I do exponents. So let's plot these points. At 0, 0, I'm still at the origin. At 1, I'm now going to be at 4. And at 2, I'm going to be up at 16. So way, way up here somewhere. Kind of like earlier, and made it narrower, right? It squeezed the function inward. Now b, the effects of b will always be referring to any horizontal changes. A helped us figure out all the vertical changes. Well, here, let's describe the function horizontally. What is happening? The points are getting squeezed inward. It's making it narrower, but horizontally speaking, it is compressing the function. So here's our first rule. If b is greater than 1, let's say in this case we use 2, but if we want to use anything greater than 1, it's going to do a horizontal compression. it's going to squeeze the function horizontally. Okay? What happens if I have like a 1/2 instead? F of x equals 1/2 squared. Now the 1/2 has to happen before we square the function because it's inside the parentheses. Yeah? So what does it look like? We have 0, 1, and 2, right? 0 times 1/2 is 0. Squared is still 0. 1 times 1/2 is 1/2. Squared is 1/2. See, 1/2 times 1/2, which is 1/4, right? And then 2 times 1/2 is 1, and then 1 times 1 is just 1. So let's graph these points. At 0, 0, I'm at the origin. At 1, I'm going to go lower at 1/4, and then at 2, I'm going to go down to 1. And I can reflect this function because it's symmetrical, and I can see that this graph got wider. But since b is affecting the function horizontally, what's actually happening to this point? The original point was at 1, 1, and it actually got pushed outward. It got pulled to the outside. Right? All of the points are going to get pulled in the outside direction. We're going to call that a horizontal stretch. It's pulling the function apart. So when b is between 0 and 1, we call that a horizontal stretch. In a little bit, I'll explain the difference between the vertical and the horizontal and how that they look similar graphs, right? These graphs look similar to each other. One of them is wider, one of them is narrower. But in terms of the language, right, we're dealing with horizontal compression and stretch versus a vertical compression and a vertical stretch. And I'll explain the difference between those two here in a second. All right, now let's talk about b being negative. Now for this one, since we're graphing it around the origin, it's hard to look at it, right? It's hard to look at the effects of b being negative. But when b is negative, we are doing a reflection over the y-axis. So now the graph is going to horizontally reflect from anything from this side onto this side. And it's easier to look at the function when it's not centered at the origin, right? If we graph something over here, you would see it flip to the other side of the graph. So here are rules for a horizontal effect. Now let's talk about those changes. We spoke about horizontal stretch, horizontal compression. What is the difference here, right? And the way I like to remember it is when I wake up in the morning, right here I'm going to draw, say somebody, let's say that this is going to be you or me or something. And I'll do a little smile that's quadratic because, you know, we're dealing with parabolas. Now here, right, we're going to be talking about the differences or similarities between a vertical stretch, a vertical compression. Right? And another word for compression would be to squeeze it or to press vertically, right? Like a squeeze. So I'm going to use my little hands here. This is my guy. He's got little hands. So if I'm doing a vertical stretch, what do you do in the morning when you stretch vertically? You stretch your hands upward. Right? And when you stretch, your hands go higher. Right? You start here on the side, and you do a vertical stretch, which means your hands go higher. And the function here, the parabola, if I extend these as my hands, the parabola goes upward. This is a vertical stretch. You're going up. Now, what is happening horizontally while you're doing that, right? The higher you go, your hands get closer and closer together. You start here and you start to stretch. So horizontally, what's occurring here is you're actually going to be compressing. right? This is a horizontal compression because your hands are squeezing closer together. And I recommend you try it right now, right? Stretch your hands up. What happens to your hands as they come there, right? Your hands start getting closer and closer together. So a vertical stretch will visually be similar to seeing a horizontal compression. Now, what happens if you stretch your body, right? Let's say you stretch your arms in a horizontal component. Now your hands are here, and I stretch my arms wide. This is a horizontal stretch, right? Now, if I'm doing a horizontal stretch, and my hands go wide, right? If my hands are going wide, wider and wider, we call that a horizontal stretch. And what's happening vertically to my hands? Instead of it going vertically stretching, I'm now making my hands wider. I'm compressing them, right? These lines are going lower. So we call that a vertical compression while I'm doing a horizontal stretch. Right? So we're kind of doing the opposite here. Whenever we stretch, we have a value greater than 1. A compression is going to happen horizontally. Your hands are going to squeeze closer together. The parabola is going to squeeze inward when A is greater than 1 or when B is greater than 1, because B is all about the horizontal change. And when you have an A value between 0 and 1, right, some sort of fraction like 1/3, the graph is going to compress. Your hands are going to go wider, which is the same thing as a horizontal stretch. So the B value will be between 0 and 1. Yeah. I hope this explanation has helped. If it did help, leave a comment or just send a quick like to let me know if this explained it correctly for you. All right. Now, let's talk about the other changes because we still have other effects. Right? The general function has an a bx minus h plus k. Now let's talk about what happens when you subtract a function. Well, subtracting a function, let's start with the parent function. Our parent function is here. And do this little point. What happens when I subtract a number? What is it going to do to the problem? Okay, so let's say that we have our parent function as just x squared, which is this one right here, right? Our parent function. What happens if we have x minus 2 squared? So let's graph it. If I put 0 in here, 0 minus 2 is negative 2. When I square that, I get 4. When I plug in a 1, 1 minus 2 is negative 1. Negative 1 squared is positive 1. When I plug 2 in here, 2 minus 2, I get 0. 0 squared is 0. So let's graph this. At 0, I go to 4. I'm going to graph this in a different color. At 0, I go 4. At 1, I go 1. And at 2, I get 0. What happened to my quadratic? I can keep adding more points, right? Like what happens when I plug in 3? 3 minus 2 is 1. 1 squared is 1. So at 3, I will get the other point. And you can sort of see how the parabola moved this way 2 units. Right? We subtracted h. This moved the function to the right 2 units. So what happens with a function if I did, let's say, x plus 2 instead? Well, let's plug them in again. Let's find out. We got 0, 1, 2, plug in 0 here. 0 plus 2 is 2. 2 squared is 4. 1 plus 2 is 3. 3 squared, I get 9. 2 plus 2 is 4. 4 squared is 16. So let's go to 0. We go to 4. At 1, we get 9, which is up here. Right? And you can start seeing how the quadratic will do something like this. Now the function moved to the left 2 units. Right? So what are the rules here? I'm subtracting h, so I move to the right. I'm adding, and I move to the left. So when we have x minus h, we're going to move to the right h units. If I'm subtracting 5, I'm going to move this origin, or this the center, 1, 2, 3, 4, 5 to the right. If I'm doing addition, right, I have to plug in a negative number to change the sign, right? Minus a negative makes it a positive, and that's how we move to the opposite direction. So here, we're going to move to the left h units. It's doing the opposite behavior, right? The general function is subtracting h, so if I want to plug negative 2 in here, right, what happens when I do that? What happens when I do x minus negative 2? If I want to go to the left, subtracting a negative would make it a positive and turn it into x plus 2. And this is why plus moves it to the left. And negative, x minus h, keeps it going to the right. So h deals with the horizontal shifts. Right? We're moving the function side to side. That is all that's happening for h. And lastly, let's talk about k. K is our last change, right? So here we're dealing with f of x equals a bx minus h plus k. K will always be at the very, very back end of our function. Okay? So let's talk about the effects. This graphic squared, as usual. Start with 0, 0, 1, 1, 2, 4. The parent function is here. What happens when I add a number at the back? So let's say that we do x squared plus 2. If I graph this function, I start at 0, 1, 2. I do the exponent part first. 0 squared is 0, plus 2, I get 2. 1 squared is 1, plus 2, I get 3. And 2 squared is 4, plus 2, I get 6. So where does this land? At 0, I'm going to start at 2 instead. At 1, I'm going to move up to 3. And then at 2, I'm going to go all the way to 6. Notice how the function moves upward. This moved up. So here, plus k moves the function up k units. What do you think is going to happen when we subtract x squared minus some number? It's going to do the exact opposite, right? It's going to shift the function, say, down 2 units. So a minus k moves the function down k units. While h moves the function side to side, k is going to move the function up and down. Alright guys, I hope this has helped. Please let me know if you have any questions. And as always, we'll calculate.